Thank you very much, Vanessa. Ladies and gentlemen, thank you very much as well to you for coming out in such great numbers. It seems that there is vast interest in what we have to say on this topic, which is great. In the interest of time, I will issue a little bit of warning, and that is that we do have a lot of content to work on today. We're going to give you an introduction to residual stresses to set the stage. We'll work on some background on eigenstrains and then present both experimental and numerical calibration procedures regarding eigenstrain tensors. Then we're going to take a little look at applications and finish off with a demonstration. So in any case, I will have to go through some of this material at fairly high speed. Having said that, if at any one point you discover a topic which piques your interest, kindly note down the number of the slide at the lower left-hand corner of the screen, write down your question and get back to us at the end of the webinar or per email or other viable channels. Right, so let me get started with an introduction to residual stresses. Residual stresses we can more or less define as stresses that occur in a component when an external load is not being applied or isn't present. They are usually superimposed or superposed with in-service stresses. There are, of course, a bunch of causes or reasons for residual stresses, and that can be all the range from non-isothermal heat dissipation, forming, local structural transformation, solid state phase transitions. It's in any case extremely difficult to produce any component that is completely free of residual stress. They cannot be considered conventional mechanical stress, and there are two fundamental reasons. One is residual stresses are beyond the standard techniques for measuring any kind of quantity, and also calculation methods. This is more advanced stuff, if you will. But the impact that these can have on the safety of affected components is characterized by a lot of complicated interactions. So it becomes at times a little difficult to predict what is going to happen. The general perception of residual stresses is that they are not predictable. And quite often it's very easy to point to residual stresses and say that this is the reason why there is a deviation or a difference between what you have calculated and what you have actually measured in an actual experiment. But on the whole, you can divide them into three groups: macro, micro, and nano level. Now, on each level, the stresses affect the behavior in different ways. So at a macro level, you might be talking about cracks, warping, and so on. Whereas on the nano scale, then we're more talking about stresses that actually impact properties of the material, among others in terms of strength. As you can see in the lower right-hand corner of this picture, there are grain boundaries with residual stresses due to phase changes. So we have both tension and compression. And this is going to cause quite a complex stress setup or a stress field. There are both positive and negative effects that residual stresses can have. It depends on what you do. On matters such as dimensional stability and fidelity, which is crucial for component assembly, you can picture it as such that if a component doesn't fit, or if you have large residual stresses and you have to bend it in some direction, then you might actually break it when you try to mount it to something. Anything involving structural integrity, fracture behavior, or among all, so I would say maybe chief among all, is the service life in terms of fatigue. Because this is where the residual stresses actually come into play. But we should say that the outcome of any situation with the residual stress is largely dependent on what kind of loading you apply. Because in general, a tensile loading tends to open up a crack, and a compressive load would then act to close them. And compressive residual stresses are usually good because they can offset or neutralize tensile stresses that would be quite detrimental in a different situation. Which is common and long-established industrial practice. If you look at, for example, the overpressurizing of airplane fuselages or the shock peening of automotive springs, are all commonplace processes in favor of using residual stresses. There are a lot of cases where residual stresses can cause the part to crack during or after manufacturing, and those problems, they're a bit easier to detect and fix up front. because you see them on the surface of the component. But there are much more severe cases where a crack can initiate below the surface and is not detected until a component has actually entered service life. And the consequences of such situations are, at best unpredictable, and in absolute worst cases they can be catastrophic. There are a little, well, not just a little bit, but there's quite a bit of material to mention when it comes to measuring residual stresses. And I'm not going to dwell on this for too long because we honestly do not have the time. It doesn't fit within the scope. But suffice it to say that there are measurement techniques that go from non-destructive to completely destructive. And that has, in effect, to do with the measurement depth and the amount of material that is being removed. Of course, this is more on the side of those kind of users who are looking into depth to try and establish some kind of reference for subsequent analyses. So this does not apply to everyone, which is why I'm glossing over this slide. There are many ways, or at least, well, I would say many, but they can be categorized into two ways of relieving residual stresses. One is by using thermal methods, and the other is by using non-thermal methods. And thermal methods, you can simply consider the same thing as when you more or less do the same thing to the material as you do to a stiff body after a really hard training exercise. You go into a hot tub or some kind of hot liquid or some kind of increased temperature environment, and you allow your muscles and bones and eggs to simply relax and go away. That's the similarity behind it. So we're not going to go into the exact detail of, for example, stress relief baking or cryogenic stress relief. This is something for a different day. The non-thermal methods that can be used are things such as shock peening and laser peening, quite interesting ways to relieve surface tensile stresses and induce compressive residual stresses instead, which is what one is mostly after. So if I summarize then, residual stresses are those stresses that occur in any component without the presence of external loads. And there are many causes for them. We have talked about them: manufacturing processes, inhomogeneous plastic deformation, material changes, and so on. They can be relieved through both thermal and mechanical methods. And on the side of novel technologies, additive manufacturing is typically one of those methods that can introduce significant stresses in a part, because you see a lot of melting and remelting, inhomogeneous cooling, and there is a lot of post-processing that goes on. There is heat treatment, there is machining, and so on and so forth. And particularly in the lower right-hand corner, you can actually see these stresses developing, but in this case particularly for a selective laser melting process. Now, jumping straight into some background on eigenstrains. Every good story begins with history, so that's where I will go first. And essentially just state that the expression eigenstrain, it's not been trademarked or anything, but it was first coined by Japanese researcher Toshio Mura in 1987. And it is an engineering concept, or an empirical concept, or experimental concept. How you want to term it is entirely up to you. It's being used to both explain and predict residual stresses and distortions in any manufactured component. Now, this is also sometimes referred to as inherent strain. You see the terms used with very wide distribution, but they mean the same thing. Examples of events that actually produce eigenstrains, as we said, are thermal expansion and or phase changes. So you can see that depending on what actually occurs, we are going to have a more or less complex mathematical description of the situation at hand. The further item to stress is that the eigenstrains themselves will generate, I'd say, more or less self-equilibrated stress fields, which you can refer to as eigenstresses. Nobody has coined the term eigenstresses. That's where they are within brackets or within hyphens. But for example, if you take a hot piece of glass and you put it under cold water, it can break because of the eigenstress field, which ensues if the thermal gradient is substantial enough. So imagine a hot glowing glass, and you simply put this into water with temperature of 1-2 degrees C, it will definitely crack. But probably the most clear and present example would be eigenstrains in welding, because during a welding operation, the heating and cooling introduces very large strains into the structure. If we're talking in a welding simulation context, then these non-elastic strains can be referred to as eigenstrains. And what needs to be said is that in this case, the eigenstrains include strains both from the thermal expansion, the phase transformation, initial strains, plastic strains, creep, and other non-elastic strain components. So you have a very complex situation overall. In a welding simulation, if you're using the concept of the eigenstrain, then the eigenstrain itself will be applied to the weld line, creating a strain field, which allows the engineer to assess the global deformation of the part. That's the idea. Now, if we consider what Toshio Mura was coming up with in 1987, well, he didn't have thermomechanical simulation on his side when he proposed the eigenstrain concept. And that can be done today. But let's think about it in a different context, and that is to determine the eigenstrain in a weld line. We create a small representative model of that weld line. And the strain in the weld line is determined on the tiny model, or a small model, I should say, either analytically or in a finite element simulation, for example, such as a fully fledged thermomechanical situation. Then what happens? Well, from the thermomechanical simulation, we can extract the inelastic strain components and put them together in what we refer to as the eigenstrain tensor. With this information, it's then possible to set up, and that's what we do, a new analysis, which is a purely structural one, not a thermomechanical one, in which the eigenstrain tensor is applied to produce the same deformation field as the computationally more expensive thermomechanical simulation in the case. So what you see here is going from a small simulation to a full deformation field on the right-hand side. Now, once the eigenstrain tensor for a particular weld line has been determined, then you can use this information for, let's say, a full size or a full scale analysis of a larger marine structure. So basically what we have is this type of panel with a little hole for, let's say, a window in this case, on the side of a ship hull. We go through a simulation where we apply the eigenstress tensor in the middle and end up with a deformation field as depicted in the right-hand side of the slide. So basically the eigenstrain is applied to the weld lines, and the distortion that we get is obtained from this relationship. If we want to look at this a little bit in a simple context, then if I can draw your attention to the image on the right-hand side, it's not an attempt to try and oversimplify what eigenstrain is, but it is an attempt to explain it in a digestible way or a digestible fashion. Basically, if you want to consider distortion due to thermal strains in an additive manufacturing process with two layers, then the first layer will be manufactured. That layer will contract uniformly because it has nothing to hold it back. That is our delta L thermal. And if we then apply a second layer on top of the first layer, that second layer will be constrained during cooling because it has attached to the lower layer, and that will cause the entire part to distort. This is basically a very, very simple and fast run through of what the whole contraction business is about here. Metal powder bed processes then are fairly comparable to welding processes because effectively there are small beads of material that are welded together to form a structure. And of course, as you can imagine, it will induce both well, not just eigenstrains, but fairly large eigenstresses. The strains are, of course, dependent on the direction of the laser, the power of the laser, the material itself, and so on. So the thermal properties of the material, or the thermomechanical manufacturing properties, are extremely vital to understand. The eigenstrain values are then, in this case, defined for each layer, and you can use them to calculate the residual stresses and subsequently determine the distortion of the part itself. brief mathematical excursion is that in a linear elastic deformation domain, then basically the stress induced by an eigenstrain can be represented as follows in this picture, where C is the elasticity matrix, E total is the total strain, eigenstrain is, well, epsilon eigen is the eigenstrain, and epsilon elastic is the elastic strain. And if we use constitutive equations like these, then the eigenstrains can be used to compute residual stresses originating from a mechanical, a thermal, or any kind of microstructural source. So it becomes a very flexible tool. The way the eigenstrain tensor, which is more or less the ammunition for an analysis like this, is defined, is represented as a standard tensor with 6 components. And as we talked about earlier, the components of this tensor are functions of many factors. So all the way from material property, manufacturing process, and thermal history, and there is so much more. Of course, there's a range of ways that you can go about to try and determine what the appropriate eigenstrains will be, all the way from destructive to non-destructive testing. You can use numerical simulation, which is probably the preferable choice in this case, or analytical formulas, but then the scenario has to be very, very simple. One has to be honest about that. Because once an appropriate eigenstrain field has been determined, and if you have put enough good work into it so that that eigenstrain field is in truth representative of the volume you are intending to use it on, then it can be applied in a layer-by-layer simulation to actually predict the residual stresses and the distortions of a three-dimensional printed component. So if we summarize then, in total, eigenstrains are an engineering/empirical/experimental concept, which has its foundations back to halfway officially 1987. This concept has been used quite a long time for simulating residual stresses from welding operations. And the components of an eigenstrain tensor are functions of a number of factors, including material properties, manufacturing processes, and the thermal history, to mention just a few. And once the eigenstrain tensor for a small scale geometry or a model has been determined, it can be used in a full size analysis, for example, of going from a small panel or a small item of a marine geometry or a marine construction into an entire structure, an entire string, or an entire panel. And with that, what I'd like to do is to hand over the word to Stephen, who is now going to talk to you about the experimental calibration process of the eigenstrain tensor.
Yeah, thank you, Anders. That was a very nice introduction. And I can imagine that you're interested in seeing how the eigenstrain tensor is actually being applied after this very nice background introduction which Anders gave us. So at this point that where you kind of know what the eigenstrain tensor is and are eager to implement it, you kind of ask yourself the question, where do I get this tensor from? And there are two ways of doing that. As Anders said in the introduction, we have the experimental and the numerical methods that are available. Let's first have a look at the experimental methods. Commonly, to obtain these values, we would use a simple setup, print test specimens, such as these simple cantilever beams, as they are depicted in the pictures here. And the procedure is very simple. We print the beams, with preferably with different orientations to obtain the deformation regarding different orientations of the beam. We use a specific scanning parameters which we need to record at this point. So we need to know what kind of laser path, what hatch pattern and so on we used at this point. Then after the print process, the beams are cut. Since we want the inelastic part, so we remove the elastic part by cutting the beams and let it expand, so to say, or to see the spring back. And then we measure the deformation of these cantilevers at the tip or along a defined line. So it's pretty simple at this point. Next step is then to correlate that to the simulation. So at this point we build or replicate the same procedure in the simulation, apply the eigenstrain method to the beam, although we don't know the eigenstrain tensor yet. But we set up the simulation at this point, we use the full material properties, thermomechanical properties, or elastic and potential in this case in our Abacus simulation, and run the simulation through a calibration workflow. So we know what the final distortion of the beam should be, but we don't know the eigenstrain tensor at this point yet. So what we do is we run the simulation, compare the simulation result with the target or the measured result as depicted here in number 4, and we try to minimize the difference between these the curves that we obtain. And you kind of see this in the screenshot here, where we use the results analytics tool in our 3D experience platform to compare the deformation of the experimental beams with the current deformation from our current simulation for a given eigenstrain tensor. That's the one depicted here in the center. And if the deformation of the difference is sufficiently small, then we accept this result, and the resulting values is actually our eigenstrain tensor. Now, commonly, we only use the main components, the 1, 2, and 3 direction of the eigenstrain tensor. The cross terms are commonly discarded, although, as you can see, it's quite easy to obtain them and use them, but they're usually so small that they are simply discarded. It's an approximation anyways. So experimentally, the whole thing is fairly simple. As said, we create test specimens. We need to print these test specimens under controlled conditions in different directions. We correlate the physical printing to a simulation, setting up a simulation, and correlate that. And at the end, we accept the eigenstrain tensors that we obtain in this way if the difference between simulation and the numerical simulation is sufficiently small. And then we have the numbers, the eigenstrain tensor, which you may apply to other specimens, other test full-size specimens as well. Now, talking about 2 methods, the other option is the numerical calibration of the eigenstrain tensor, which is possible if we have access to a full thermomechanical simulation. So in this case, we have actually 2 possible approaches that we will discuss today. One is the micromechanical approach, where we use a small cube representing our material. So we print a small cube with the designated laser pattern that we have in a full thermomechanical analysis. And we use the results of this analysis, the strain field of this analysis, to determine the eigenstrain tensor. Similarly, as for the physical simulation that we physical print that we just saw, we could replace the physical testing with a simulation that is shown here in the lower picture, where we print test specimens. They can be cantilevers as shown here, or can be virtually any other structure that's convenient to use in this context, in a full thermomechanical simulation. And from that thermomechanical simulation, we use the result as the reference value in a calibration analysis, similar to the one that we just saw. The difference that we replace the physical testing with the numerical analysis. Here's the example. Let's first have a look at the unit cube analysis. So we're printing a small patch, commonly a unit cube. It doesn't not necessarily have to be a full cube, but has to be sufficient to, the size of this cube or region has to be sufficient to represent the actual micromechanical field and the laser field. So if we have a simple meandering laser, then the field, the cube can be rather small. If we have a more complex chessboard or a random chessboard pattern, then the representative unit element should of course be sufficiently large. As you can see on the list here, we need to include all the parameters that we would use on the physical machine as well. So the laser power, the spot diameter, the hedge distance, motion, whether it's back and forth or unidirectional or whatever direction, recoding time, because that allows the material to dwell, and so on, and put that into our simulation. And at the end of this simulation, we're just seeing this as an animation here. We get, oh sorry, that was one too far. We get the results. So the simulation yields, of course, the temperature field. And the temperature field in the sequential thermomechanical analysis is the input for the structural simulation. So after having obtained the transient temperature field, we put that into the structural simulation, which gives us the displacement and stress, as we can see in this image here. And as a side effect, so to say, of the simulation, we obtain the strain field. And from the strain field, we extract the inelastic part, which gives us the eigenstrain tensor for this representative unit cube. And assuming that whatever happens in this unit cube will happen to our full-size part, we can use this information, this eigenstrain tensor, and apply it to our full-size part. Now, similarly, as we've seen for the physical simulation, we could print test specimens as shown here. So we're printing, so to say, full-scale beams and doing it in the same manner as we did for the unit cube. Now with the difference that this is not a micromechanical view, it's more a macromechanical view, because we're not looking at very small cubes, we're actually looking at, so to say, real-sized parts. Again, we use a sequential thermomechanical analysis to print these test specimens, considering things like the laser path, that is of course important in this condition, the laser pattern, laser intensity, and so on. We're letting it cool to room temperature, just as we would do in a physical simulation, and then we cut the beams and measure the deformation at the tip or any other location of these beams. So that gives us the reference. Again, the simulation yields, of course, the deformation of the beams as shown here, and the stresses as which are, yeah, in this case they're not strictly not needed, but it just comes out. After, again, we cut them and measure the final deformation again to obtain the inelastic part of the tensor. And as we did see previously, we put that into a calibration loop where we again run a simulation of the test specimens, whatever direction, whatever form they are, and compare that to the difference versus not the physical testing, because we want to skip the physical testing at this point, but we compare it to the numerical simulation, the thermomechanical simulation, and again do a calibration analysis and optimization, so to say. And if we're sufficiently happy with the result, then this gives us the eigenstrain tensor to work with. Most of it. So, putting it together, we just saw that we have looked at two different methods of numerical obtaining the eigenstrain tensor that can be done on a unit cube analysis in a micromechanical level, or it can be done on a more macro scale analysis like this one, where we print test specimens similarly to the ones that we may print on a physical machine and evaluate the simulation to obtain the eigenstrain tensor. So now we've learned where the eigenstrain comes from, we've learned how to obtain the eigenstrain tensor, and the next step will then be applying it to real-sized or to other parts. And in this section we will be looking at two examples for that. So this is the first, a very simple example, just a random structure here, and the eigenstrain tensor that is represented written here. Now this section actually talks about transitioning from the small model that we just saw to a real-sized model. And that does not necessarily have to be a one-on-one thing, because the eigenstrain method itself is approximative, so there may be some difference. And since I personally think that is important to keep in mind, we'll look at two examples here. So the first one is this little structure we see here, and in this case we can actually see the comparison between the thermomechanical analysis and the eigenstrain analysis of the same part, and we use the approach to obtain the previously discussed numerical approach to obtain the eigenstrain tensor. And as you can see, the results are quite good in a way that the deformation field is represented properly using the eigenstrain analysis. We can see the maximum locations are in the same position, same location. So we are happy with that. Looking at very detail, we can see that there are still some differences between the deformation fields, so it's not necessarily a one-on-one match. The match for the cantilever beams that we used to determine the eigenstrain was much better than for the full-sized part. So we have to accept some difference. This is the turbine blade, and we've seen that previously too. And again, here we use the results from our calibration to apply that to our full-sized model. So we ran the calibration. In this case, we actually ran the calibration versus physical testing, and we had now using the finite element model is just the structural model, is the eigenstrain model, and run against it. And again, for comparison, simply because it's available in our simulation, we compare it again to a thermomechanical analysis and compare the eigenstrain analysis. And again, we find that the deformation fields agree quite well qualitatively. So we find the same overall deformation field, the hot spot, so to say, is in the same region, but there are some differences in the magnitude of the displacement. And again, the match that we had obtained for the eigenstrain was for the simple cantilever. That was a very good match. Now for the full-sized part, we can see that there are some differences. So we're not getting a 100% predictive hit in this case. Moving on, we'll look at some examples on how to use the method and some details that may be of interest. So the first thing we were looking at here is how to set up a simulation. What we do at this point is we would create we take our part, and that's shown here. It's the cover for some pump cover that's printed here. The dark strains here, what looks dark is actually the support structures that were generated, and we see the build tray, the build envelope depicted here, the recoater, and the gas flow direction. So the full setup has been done. We did create the print path. We created it in our software as well, in 3D experience, as you can see here. So we're ready to do the actual print, or we're talking about simulation today to do the simulation, because this input will be used there. A few words about meshes. It is very common to use a voxel mesh in an eigenstrain type analysis simply because it is simple. So the voxel mesh offers the benefit of being able to mesh virtually any structure without some hassle about choosing the right element type, element size, and whatsoever, or refinement or whatnot that is involved in a classical finite element analysis. Yet the drawback is, and you think we can see that quite clearly here from the detail, is that it does not cover or capture the detail very thoroughly. For example, the circular rounded non-planar structure is not captured accurately, and the support structures are not captured very well. But for an approximative analysis, which this eigenstrain approach is, it is good enough. Still, oh, sorry, I was too fast here. Still, we can go on back. That's the slide I want to show. In our software, we have the opportunity to use other kinds of elements. We just talked about finite elements, and here's just a simple example showing that we can do the same kind of analysis, the structural analysis, using the eigenstrain approach, using non-voxel meshing techniques. So we can use tetrahedral elements or hex elements adjusting to the or joining to the actual structure. We can use shell elements if that is needed for small support structures and so on, and to actually get a somewhat better representation of the field, again with the eigenstrain approximation kept in mind here. But as we can see, the result is much closer to the actual structure and adhering to the structure. Another approach that could be used when we do the voxel approach, which is easier to handle for the not so seasoned simulation engineers, so to say, would be to simply map the results onto the physical structure or the geometry, which is possible as well. Again, approximative. So here we look at a small video showing how we would set up the analysis. So again, we have this tube junction model used here, and we have used put it on the build tray. We can see the arrow indicating the gas flow direction, which may be interesting. We can see the recoater, and we can see here, again, this is on our 3D experience platform, that we have defined a laser path, which in this case, for this kind of analysis, it may be used. We have a technique where we can assign eigenstrain according to the laser path. So you could have a different eigenstrain value, a different eigenstrain tensor, for example, in the surface versus the hatch pattern in the center. But here we just needed to define the simulation time. And from then on, we simply switch to the other application, which is our distortion checker. We use the information that we just produced for the simulation. We can define a slice thickness, and that is actually all at this point that is needed to run the simulation. We have the option to modify the mesh density or the mesh size, and for the sake of demonstration, we did that here. You simply select the mesh, hit the simulate button, select the number of cores to run on. That can be done locally on my workstation, or I could use a simulation cluster, HPC for that, and submit the simulation. It's as simple as that. So there's not more needed to actually define the simulation job. The meshing is taken care of automatically. In this case, again, we're looking at the not simplified. We're looking at the voxel mesh for that purpose. So easy and simple. And looking at the results, this is what we would get after the simulation. Again, we see the part that is shown here, now represented with this voxel type mesh. And we have, of course, our known simulation results, such as the displacement result, which you can look at, it's shown here. And if we're interested, then we can have a look at the stress field. So all this data is readily available. The simulation is a purely structural analysis, so it's very fast as compared to the thermostructural analysis, which takes more time. And it gives us a good overview of what to expect from the simulation, from the part, whether it's printable or not. The results, again, are shown here. Just for comparison, again, we're looking at here, it's on the voxel mesh, but we just saw it's possible on a non-voxel mesh as well. So the results are the displacement field, of course, which is interesting to use. And the stress field, I think it's quite interesting to see, or quite easy to see here, that the stress field for such a voxel mesh may not be as exact as for a non-voxel mesh, but for an analysis where the question is whether the part is printable at all or not, this kind of simulation and analysis may be sufficient. So, putting it together, and that's actually the content of today, is we had a look at inherent strain or eigenstrain methods, and with the introduction given by Anders, we learned that it's an engineering concept, so it's not a scientific method, the eigenstrain, it's an approximative method, and it makes life easier because, as we saw in the example of the weld simulation, the full-size ship is very hard to simulate on a in a full-scale simulation, especially 1987 when the eigenstrain concept was devised. That was not possible, but today we can have the option to run a full-size ship, but maybe want to do an estimate with the eigenstrain analysis. We had a quick look at eigenstrain calibration procedures. That was the for one, the experimental method that is can be used where we print specimens, measure the information, and then relate that to the simulation results. Or we can could have a look at purely numerical procedures, such as the micromechanical procedure on a small cube, or the replication, the mimicking of our physical testing in our simulation. We had a brief look at some application examples, the turbine blade and the triangular part that we looked at, and we discovered that there is good agreement between the approximation given by the eigenstrain method and the physical testing and or the thermomechanical analysis, but we have to accept that the eigenstrain method is an approximative method, so there may be some differences there. And finally, we had a quick look at some software demonstration, the way that the eigenstrain method for additive manufacturing is currently implemented in our 3D experience platform simulation at this point. Now, at this point, I'm clicking to the next slide and handing over back to Anders for some closing words on this section.
Thank you very much, Stephen. That is a very comprehensive, very collated, very concise version of an altogether actually quite complex topic. If you want to go and read the paper by Muda, then by all means, it's 77 pages and mostly mathematical stuff. So if that is not quite your fancy, then maybe have somebody read it who likes math and then have them tell it to you. But more importantly, you've seen the stuff that we say are possible to do with the implementation of the eigenstrain methods on our side. But there's so much more that you can do, more hot stuff, really some hot stuff. Apart from the usual suspects, I would say, of lattice design and support optimization, we have disclosed to you our attempts of properly dealing with eigenstrain and validating. Validation is always something at the top of our list. That is how we make sure that we deliver the best possible experience to our users, is to make sure that the physics that we put in are also validated. On the hot side, though, there are matters such as heat treatment, which you can deal with in the scope of the framework for additive manufacturing simulation, but also things such as distortion measurements and validation. It offers you a plethora of capabilities to take experimentally deduced values and compare them to the numerical results. And as a final note, maybe on this page, which we haven't talked about at all, is the fact that machining comes into play. Well, machining, for one, is not simply the matter of taking away material for removing the part once it has been printed. You can also consider cases such as hybrid additive manufacturing, where layer by layer or a number of layers are being manufactured, upon which a mill comes in and makes sure that the geometry conforms to a specific tolerance level, and that in turn will also induce heating and so on. So any operation carried out will do something to the stress field, to the strain field, and also to the structure of the material itself. But these are all topics that the framework for additive manufacturing simulation allows you to handle. So where to go from here? The first place, if you're curious, is to go to our microsite called Print to Perform. That's the name for our solution for additive manufacturing. And you can use the QR code on the right-hand side, or simply type in the URL as we have listed at the bottom. And it turns out that we have indeed held good pace today, so that at this stage I would, on behalf of Stephen and myself, like to thank you immensely for your kind attention and patience. And we will now open up the floor for questions. So again, thank you very much for your attention.